Hello, continuing in nuclear and particle physics and maybe radioactivity. We've got here just the two questions, I think, this time. We've got to fill in this table here of quark composition and charge for neutrons and protons. So a neutron is up, down, down. Proton is up, up, down. Charge on a neutron is 0. Charge on a proton is +1e. Now we're on to these quarks. We've got a similar-ish sort of table here. Charge on quarks, up is 2/3 of E, down is -1/3 of E. Baryon numbers, actually this is something we haven't spoken much about with baryon numbers. So for quarks, they're all +1/3. For antiquarks, they're -1/3. So if you've got something like a proton or a neutron where you're adding 3 of these quarks together, then you get a baryon number of 1. If you've got a meson, which is a quark and an antiquark, then they're going to cancel out and you'll get a baryon number of 0. So yeah, that's what's going on with these baryon numbers for quarks. If you've got other weird exotic particles, then you just add up the baryon numbers as required. And they're all conserved in any of these equations. Any kind of quantum event, you have to conserve baryon number along with pretty much everything else. Strangeness, neither of them are strange. So I don't know why they're desperate to put in strangeness at times, because it's something that, I don't know, they include this in some questions on some exam boards, but it's so little discussed as to what it actually means. It's just adding it to a list of properties that get conserved. But there you go. Anyway, I fill that one in and then move on. When a neutron decays, it can produce particles that include an electron. Complete the decay equation below for a neutron, right? So we know we're going to get a proton, we're going to get an electron, and then we're going to get an anti-neutrino, an anti-electron neutrino. Name the interaction responsible for the decay of the neutron, so that is weak interaction. Electrons and neutrons belong to different groups of particles. Name the group of particles to which each belongs. Right, so electrons are leptons and neutrons are baryons or hadrons. Either one is the same. You know, made of quarks and having 3 quarks. It's but yeah, a neutron is both a baryon and a hadron. So yeah, that was a nice, just a quick set of definitions really on things. Right, the next one. Describe what is meant by the spontaneous and random nature of radioactive decay of unstable nuclei. Right, so the spontaneous bit, so that means that it's you can't change it. It's not induced. It's something that's just happening independently. So you cannot induce, cannot be induced. It's immune from sort of in external effects. So it's not like where we're inducing a nucleus to split if we're having induced nuclear fission. This spontaneous radioactive decay is just something that's going to happen. You can't affect it. You've got this you know, this unstable nucleus, and that is what's going to happen to it, you know, regardless. So so that's the spontaneous bit. For the random, we're looking at, we don't know when or where or which, I suppose. We don't know which nucleus is going to be the next one, and we don't know when any particular nucleus will decay. So it's random in both things. So if you're looking at the whole set, we don't know which one out of the whole sample, we don't know which nucleus is going to be the next one to go. And if you're looking at one particular nucleus, then we don't know when it's going to happen. So that's why it's all random. Define the decay constant. So that is the probability of decay per second for a nucleus. Yep. So explain the technique of radioactive carbon dating. Right, we've done this one 1 or 2 times before. So this is where we've got 3 things that we want to say. We've got the I suppose this isn't really part of the technique, but we're saying that the living things are absorbing the carbon-14, absorb carbon-14 until death. And then so when it dies, it's got a particular ratio of carbon-14 to carbon-12. So then we can say that the carbon-14 will decay. So we can compare, let's get that out of the way. So yeah, we need to compare the ratio of carbon-14 to carbon-12 in the sample versus something living. So we take something living in the present day. So, and we can use those two ratios along with our decay equation, the n equals n0 e to the minus lambda t. I mean, this n can stand for all manner of things in these decay equations, whether it's the activity, whether it's the number of carbon-14 nuclei in the sample. We can use this because we're seeing how this has changed, how the number of carbon-14 nuclei have changed. So we can plug that into here, comparing what we currently got to what we have in something that's living, and then that will give us the time. The activity of a sample of living wood was measured over a period of time and averaged to that activity. The same mass of a dead sample of wood, measured in the same way and given that. Half-life is that. Calculate the decay constant in years to minus 1. Right, that makes things a bit easier because we can just say that it's log 2 divided by 5,570. We don't have to convert things into seconds. Type that into the calculator. We're getting 1.24 times 10 to the minus 4 years to the minus 1. So what is the age of the sample of dead wood in years? So we're doing everything in years. Let's just stay in years then. So let's come to this. We can say that the activity over the original activity is equal to e to the minus lambda t, where we're doing all of our time in years and our decay constant in years. So if we rearrange all of this, let's do a rearrange. So t is going to be the natural log of, well, we'll flip that upside down so we can get rid of the minus sign here, and then divide by that constant, the decay constant. So typing all of that in, we get 2.01 times 10 to the 3 years. Are we okay to go to 3 significant figures here? They've given us 3 significant figures everywhere else, so yeah, we seem to be all right to do that. Suggests why the activity was measured over a long period of time and then averaged. Right, well, we've got very low activity here. So, and we've got this random nature. So if we've got we got random low activity. So we want to get as many samples as possible. So we need a long time to get a high number of samples, to get large sample, large data set, yeah, I mean, that's the main thing because the activity is so low. I mean, if you've got barely any of these things kicking off, you know, we're having to wait 5 seconds to get one decay. So if you're only getting one decay every 5 seconds, I mean, blimey, you don't want to base too much on that. You want to get a good chunk of decay, so you want to do this over a long time, relatively speaking. Right, so yeah, we've just got the last bit then. Explain why the method of carbon dating is not appropriate for samples that are greater than 10 to the 5 years old. Yeah, by the time you get to that point, we've already got low activity. And then so we can say, yeah, when t is greater than 10 to the 5, the activity is so low that it's hard to distinguish it from sort of just background readings of carbon-14 that's just, you know, around about in the world. Yeah, this stuff is going to appear in a lot of things that yeah, it's then hard to distinguish. Well, I don't need to write that out. You know, we've got this. Everything has got this carbon. Well, anything that's carbon based or has got a carbon content is going to have carbon 14 in it. And you think, you know, all this stuff is decaying off. By the time you get down into this sort of flat area, you've got loads of things that are on this flat area, whether it's millions of years or you know, 10 to the 5 years. You can't really tell them apart. It's become so low that there's, you know, what is there to actually base your measurements and calculations on here? You need to have a little bit of flex in this. You still need to be having a bit of gradient on your decay, which we would have lost by the time we've got to that point. So that is a big limitation for carbon dating, but you know, it's great for stuff in the meantime if you're wanting to date stuff which is a little bit more recent than that. Cool, so that's wrapped up those two questions. Quite a quick pair, but that was a nice one, the second one. Quite a lot to cover there.